Have you ever walked down a crowded street and suddenly felt an overwhelming certainty that you've been there before? According to theoretical physicist Michio Kaku, that feeling of déjà vu might actually be memories leaking over from a parallel universe. In 2017, a bizarre case went viral on Reddit. A woman received a text from her husband's number asking, "Who is this?" while he was fast asleep right next to her, his phone sitting untouched on the nightstand. When she asked what name her number was saved under, the sender replied with the exact secret pet name her actual husband used for her, Wi-Fi with a heart. Theoretical physics offers a wild explanation for glitches like this. For a brief moment, the timeline of our universe crossed paths with a parallel one, temporarily connecting her phone to an alternate version of her husband. While these stories are captivating, they remain anecdotal. A creepy text message or a weird feeling on the street provides no hard empirical data to prove a multiverse actually exists. To find that proof, we face a major physical limitation. We can only observe what is inside our own universe. Even with powerful telescopes, our vision is locked within this glowing sphere of light, surrounded by a dark, inaccessible void. This observational barrier once trapped the multiverse realm of pure mathematical hypothesis. If we cannot see past our own cosmic horizon, testing what lies beyond it seems impossible. Recently, a team of scientists at Italy's Trento University bypassed this limitation. Instead of looking out into the infinite void, they decided to look inward. They realized that to see how a multiverse forms, they didn't need a bigger telescope. They needed to build a miniature, quantum-scale Big Bang right here on Earth. The researchers began by cooling sodium gas to near absolute zero. This created a Bose-Einstein condensate, an ultra-stable, uniform state of matter that effectively mimics the conditions of space immediately following the Big Bang. They then applied a massive magnetic field to the gas, forcing every single atom to perfectly align in the same direction to create a completely unified environment. To simulate the raw energy released at the dawn of time, the scientists bombarded this stable gas with a highly specific frequency of radiation. The energy forced the atoms into a quantum shortcut. As the radiation hit, specific clusters of atoms magnetically flipped, forming isolated, highly stable bubbles directly within the glowing fluid. In physics, this transition represents matter migrating from a fragile false vacuum into a more stable true vacuum. This experiment physically demonstrated that injecting intense energy into a uniform space triggers the formation of stable pockets of matter rather than just a uniform expansion. What these physicists achieved in the lab is the physical realization of a mathematical theory proposed in 1977 by physicist Sidney Coleman. Coleman proposed that the Big Bang was a rapid expansion of empty space, a highly unstable state that needed to lose energy to find balance. He used the analogy of boiling milk. If you watch a pot heat up, you'll see a cyclical process where fluid warms, rises, cools, and sinks. But through quantum tunneling, matter takes a shortcut, forming bubbles that reach a stable state instantly, bypassing the slow cycle entirely. Following this logic, the extreme energy of our early universe did not cool down uniformly. It boiled into infinite, localized pockets of stability. If we scale the Trento lab experiment and the boiling milk analogy up to the size of the cosmos, the implications are profound. This model suggests that our specific universe, containing every star and galaxy we know, began as one of those stabilized quantum bubbles. In this framework, the multiverse is the greater boiling pot of spacetime, the landscape containing our isolated bubble alongside countless others. Proving the physical mechanism in a laboratory is a significant milestone, but we still lack a direct observation of other universes in space. If infinite bubbles expanded during the Big Bang, some would have inevitably bumped into ours. Those collisions would have left physical scars or bruises on the boundary of our universe. This map shows the cosmic microwave background, the ancient radiation left over from the Big Bang. Physicists are currently searching these modeled temperature fluctuations for signs of those cosmic collisions. Despite having this treasure map, we haven't yet identified a definitive scar from a neighboring universe, leaving a gap in the absolute proof. This missing evidence might not be due to a lack of scars, but rather to flaws in our baseline calculations regarding the age and light of the universe. New observations from the James Webb Space Telescope are currently challenging standard cosmological models, providing data that suggests the universe could be twice as old as we previously thought. If our estimates for the age of the universe change, we must reevaluate our analysis of the microwave background. The proof of other bubble universes may already be hidden in this data, waiting for physicists to adjust their models and find it. The multiverse has moved from a Reddit mystery to a testable laboratory fact. By looking through the right lens, we may soon confirm that we were never alone in the void.